Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the Director of Content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
Thanks again, Derek, for hosting, and thanks to Christian and Isaac for joining. And we have a special guest, David Schneider.
Hello.
Thank you, David, for taking time out of your schedule to talk with us.
No problem.
Isaac had a request at the end of the last podcast that we talk about the knots as processes idea. What we'll do is I'll just sketch out the overall result that we were aiming for, and then we can talk about some of the subtleties, like the approach, like how we worked out the approach, and then some of the subtleties, and what that did in terms of how we worked on the proof. Does that sound like a game plan for everyone?
Yeah, sounds good to me.
Okay, awesome. As I mentioned last time, the motivations that I was interested in was bringing biosimulation to mainstream mathematics. I think biosimulation is a really key proof technique, and this was kind of inspired by folks like Herlihy and others and Goubot and folks like that who are bringing algebraic topology techniques over into concurrency theory to try to use some of those proof techniques. And I was like, well, but concurrency theory has biosimulation. You guys need that.
Right.
that was the idea. And so I thought, well, let's do something simple first, and something a result that's kind of already known, because it was known in the 60s that ambient isotopy is decidable, and so it shouldn't be too surprising that you could get a result with biosimulation. And so the thought is you give encodings of knots as processes, and then the theorem is two knots are ambient isotopic, which is the notion of equivalence in knots, if their encodings as processes are weakly bisimilar. So that's the result that we were aiming for. And the trick how to do this, well, it turns out that ambient isotopy is equivalent to being able to transform a knot diagram of a knot into the knot, so let's say we have knots K1 and K2. So if I take a knot diagram of K1, and if I can use the Reidemeister moves, which are these specific kinds of, you could think of them as graph transforms, which transform the knot diagram, in very specific ways. So if you can construct a sequence of Reidemeister moves from the diagram, a diagram of K1 to a diagram of K2, then the knots are ambient isotopic. Does that make sense?
Yeah, it makes sense to me.
I bet it does to you.
Yeah.
So one question that I had is, did they prove this decidability of the ambient isotopy to did they prove that using the Reidemeister moves?
Decidability was done via the Reidemeister moves. Basically, Reidemeister moves are the name of the game in most of these things, at least as related to computability.
Yeah. I think that originally it was this guy named Hawken he did it back in 1957, or it was right before I was born. That's how I remember. So, and then and he used like three-dimensional topology, which does use knots a lot, but there's actually a lot of other proofs now too. So there's some other proofs that don't use you don't have to.
So do the Reidemeister moves correspond to certain congruences in the calculus?
Not exactly. They're not at the congruence level for the calculus, but they end up being transforms on processes that are property preserving in a particular way. So then the other piece of the puzzle that is necessary, now all we want to do is just to encode a knot diagram into a process, and that's a lot easier than encoding a knot into a process. Because a knot diagram is essentially, is it quadrivalent graph?
Yeah, quadrivalent. Yeah.
Yeah, it's a quadrivalent graph. Yeah, I was just
depending on who you're
I was
talking.
counting the number of incidents into the vertex there in my brain.
Right.
Yeah,
Well,
and
that's considered a good knot diagram. You can have lots of knot diagrams, but quadrivalent is the one that everybody's expecting.
What is a quadrivalent graph?
Yeah, I was just about to ask.
Yeah.
Oh.
Every node has 4 edges.
Okay.
Yeah.
Yeah. So you project the knot onto a plane, and there's lots of ways to do that. But if it's most of them, what they call general position, you're going to have nodes that have just 4 edges coming into them.
Okay, and 4 is important because that represents a crossing of
That's
like
right.
two pieces of the knot or something.
that's exactly right. Yes.
Yeah. Okay. Cool. Oh, perfect.
It typically
That
it'll
totally
be
makes sense.
drawn where 2 from opposite sides, so to speak. They usually separate each other. So the one of them will be broken, so you can see which one's the over.
Yeah. Right. One goes under, one goes over, basically.
Yeah.
Right.
Yeah. Exactly.
Right.
It's really interesting if you look at these in the light of proof nets. They're suspiciously similar to proof nets in the sense that you're visiting these things in both polarities. Right. So Girard's long trip condition on proof nets is something that there's a version of that holds for knot diagrams, which also shouldn't be too surprising given the decidability. That's a digression. In general, there's a way to convert every graph, not just the quadrivalent graphs. There's a way to convert every graph into a process. And there are lots of different ways to do that as well. Cardelli, Gelly, and Gardner gave one encoding. Our encoding is a little bit different. You can use these different encodings to go after this problem. I was interested in a circuit-like encoding that sort of had some other intuitions behind it. So if you just look at the diagram of a crossing, you can think of this as like a circuit. So picture in your mind's eye, you've got 4 terminal points on this circuit. So you just got a rectangle, and there are 4 terminal points on the rectangle where we might attach signal. I'll label them. Let's say for fun, we'll label the rows X1 and X2. So the top left is X1, and the top right is X2, and then the bottom left is Y1, and the bottom right is Y2. And you can imagine that these might turn into channels and processes. And then the idea is that we want to model signal flow from these terminals, from one terminal to another. Canonically, we might connect the X2 terminal to the Y1 terminal, and then we can connect the X1 terminal to the Y2 terminal. Does that make sense?
Yeah, so we get one of these crossings.
And now, to make it a crossing, what we want to do is say that the signal going over one of those diagonals is always free to flow, and the other one has to wait, so that if there is signal going through that wire, then it must be synchronized and wait for the signal to flow. So it's like a traffic light. Does that make sense?
Yeah, and so this is kind of to distinguish between the overcrossing and the undercrossing.
Right,
wires,
exactly right. So the overcrossing always gets to just go. So if you have some signal arriving at X2, then there's no additional synchronization to get over to X1.
Okay.
I'm sorry, Y1. And then when you have signal, and it works bidirectionally, right? So if you have signal arriving at Y1, there's no additional synchronization required in order to get the signal coming out at X2.
Yeah.
Are the nodes the processes and the wires the channels? Or?
Something like that. So essentially the wires, you're going to think about it slightly differently. You're going to think about a process that represents the circuit that we just drew.
Yes. Okay.
You can decompose a knot diagram into a bunch of these circuits that have all been wired together. Does that make sense?
Yeah, definitely.
Without peeking at the paper, I would encourage people to write down a pi calculus or row calculus process that does that models that circuit that we just described. You know that you really grasp pi or row if you can write that circuit down. I used Dowker Thistlethwaite codes to provide an algorithmic representation to wire up the diagrams correctly, wire up all the crossings correctly. If I just give you, like they're in crossings, well, that's not enough, right? You need to know how the crossings are wired up, because for example, there are lots and lots of 9 crossing knots. For people who are interested, there's a beautiful site called Knotplot, which provides a little zoology of all the crossings. The trick is you have to figure out how to wire up the crossings. And there are lots, as I said, there are lots of knots for a given number of crossings. And as the number of crossings goes up, there are more and more knots that have those crossings. There are different encodings for knots. I use the Dowker Thistlethwaite codes to give me a spec that I could just walk over and then calculate the wirings. That's another piece of the puzzle that you need. But I strongly encourage people to look at this issue of writing down one of these circuits as a process, and then writing down some encoding of how to wire up the crossings together. Once I had that, the proof looked relatively simple. And then David said, "But what about?" And then he mentioned this phenomena that I had never encountered before. David, you want to talk about Perko pairs?
Sure. Okay. Yeah. Well, I don't know how much of the history we on. It's pretty interesting, actually. But
actually, as much as you want. I think it'll be a lot of fun for the audience.
Yeah, I second that.
Yeah, I mean, these things are kind of interesting to look at. But it kind of originally, you kind of, to see the whole storyline, you go back to P.G. Tate. I forget what the P is for, but he was studying with Lord Kelvin. Well, he was inspired by Lord Kelvin to look at knots. Kelvin thought knots were at the core of chemical units. I don't think I have the atomic theory quite yet. So anyway, but Tate made this big table of knots, and basically he went through by hand and made all these 4-valent graphs, and then just played around with changing crossing, making them over crossings or under crossings, looking at all the possible things. And I think he went up to 11, or was it 12? Anyway, and he made this table. And then a student of his called Little proved something called Little's theorem, which turns out it was false. But he had a theorem that said that if you have a knot where something called the writhe, you travel along a knot in a certain direction, along the diagram in a certain direction, and whenever you come to what's called a right-hand crossing, like when you go over an overcrossing, and the undercrossing is going to your left, that's negative, and if it's going, that's positive, and then if it's going to the undercrossing is going to your right, then that's negative, and then you just go around and count every time you go over an overcrossing. You count all the positive crossings as pluses and negative crossings as negatives, and total that up. You get what's called the writhe of the knot. So Little claimed that he had proved that in 1899, this is that writhes characterize the knots, basically, or that it's a knot invariant, so that a knot will have, so you look at anyway, at the minimal writhe you can get out of any of the diagrams for knot, and that will be unique. And that's what ends up being false, it turns out. But so anyway, there's this thing called the Perko pair. It wasn't discovered until the early 1970s by Kenneth Perko, who was a undergraduate at Princeton, and Princeton has a really strong tradition in geometric topology and knot theory. And I think he was working with, I don't remember, he had done some work with Milner, but somebody told him, was like, well, go through this table and understand how Conway had calculated various of these invariants for the knots. So he went through and found in the 10 crossing knots that have 10 crossing in their minimal presentation, that there was actually a duplicate pair that had escaped notice for basically 100 years. So it's called the Perko pair. Yeah. So, and actually, it should have, well, I'll say it's like there was a guy at Princeton before Alexander who was kind of in the 20s and 30s. He's a giant in geometric topology. And he had calculated these things called Alexander polynomials. I mean, it was kind of a brilliant idea, really. You calculate the polynomials, and the polynomials are different, then you know you have two different knots. But it is possible for two different knots to have the same polynomial. So it's, you know, it's not an invariant. A total invariant, right? Like it doesn't identify them. It goes one way, but not the other, right? So, yeah. And so basically, you know, Conway, when he was a high school student, went through Tate's table with the 11 crossing knots, and he calculated the Alexander polynomial. I was like, whoop, there's some duplicates, and he got rid of those duplicates. Apparently, he didn't look at the 10 crossing knots. So then Conway's table made it into this textbook by this guy named Dale Ralston. It was kind of like a Bible of knot theory for a long time. And I actually have that original copy from 1976, and that pair made it into this table. But I think it was, anyway, somehow it wasn't, by the time Perko had discovered this, anyway, it made it into this book. So it was kind of a big deal, I guess, that they had found yet another pair. That just shows how hard knots are, I guess, you know, but it took them that long to even notice. I mean, plus they were having to do all this stuff by hand, so, you know, it wasn't, it's so exciting. Ugh. You know, it's like now, I mean, at least hopefully with this too, you can automate. There's definitely, they have programs now, and I think they're up. I don't know if they've actually counted all the 18 crossing knots yet. I know for sure they've done up to 17, and it's huge, and it just gets very complicated very quickly.
So,
and I think there's an exponential algorithm for numbering these things.
So do we still not have a systematic method of classification?
Yeah, not really. It's like
it's a really interesting point that you raised there, Christian, because one of the things that I wanted to provide was, one, a shift in the perspective on invariance. Like if you think about it, whether you're talking about the Alexander polynomial or the Jones polynomial, there's something interesting about polynomials, right? Because polynomials have a notion of dynamics baked into them, but that's not the way in which the polynomial is being used as a not invariant. And I was really interested in invariants that are about behavior, like the behavior of the algebraic gadget is the thing that is the invariant of the knot, right? So in some sense, it's shifting from this view of the knot as a static thing, just sort of hanging out there in space, to something that is dynamic. So there's signal flowing around wires. Right, so it's a very different way of viewing the knot. So the invariant becomes a different kind of invariant. Does that make sense?
Yeah, it's funny because that seems more consistent with how to view a knot anyways, because everything I'm looking at is like start at some point on the knot and start traversing it in a particular direction. It's like that's a signal, you know?
Yeah, exactly.
Right.
That is exactly that's exactly right. But as a result of this shift in the way we think about the invariant, this other thing comes along for free, and the thing that comes along for free is the application of the spatial logics and the Hennessy-Milner logics, right? Because they classify processes. Right. So in fact, you have these lovely theorems that processes are bisimilar if and only if they satisfy all the same formulae. And if you also have a theorem that says two knots are ambient isotopic if and only if they're bisimilar, then we get the Hennessy-Milner logics classifying the knots, right? It's a systematic classification system.
Yeah.
I guess there actually is a classification, some type of classification. I don't know if it's real helpful, but basically every knot is determined by its complement in three-dimensional space as well, you know, but just changes it to another kind of hard problem.
You push the bubble to a different part of the carpet, right?
Right, exactly.
So each polynomial would determine a certain class of processes?
That's one direction, but again, as I said, I'm less interested in that direction, sort of the application of the invariance from algebraic topology, or knot theory in particular, over to process land. I'm more interested in processes and Hennessy-Milner formulae applied to knot theory and topology land. Yeah.
Mm-hmm.
I was just wondering what you meant by the polynomials having to do with dynamics.
Well, I'm just saying that inherently, there's a notion of dynamics that comes from a polynomial. You can run a polynomial. we can calculate. Like I plug in a value for the variable, and I get a number out, right? So it is a program, but that programmatic aspect of the invariant is left by the wayside. We just look at the structure of the polynomial.
Yeah.
And this is what's so interesting is that I think that ever since Lambda, something has been staring us in the face that we're not seeing how important it is, and that is the structure function relationship. Like, and this like if you just shift sciences for a minute, right? I mean, when you move to a place where telos and purpose is the name of the game, then the structure function relationship leaps out in stark contrast. If you're trying to understand an organism, or something as simple as a virus or a bacteria, the structure function relationship is essential. Like understanding how its structure gives rise to its behavior is part and parcel of biology. You don't have a good biological account until those kinds of questions, you have some kind of handle on those kinds of questions. But in a mathematical context, a lot of that gets lost, right? So the structure function relationship of the polynomial is not giving us the same kind of information about the knot. Whereas the kind of invariant that we're calculating with a process, the kind of knot invariant that we're calculating with a process, it does have the structure function. First of all, with lambda and pi and all of the computational calculi, the structure function relationship is right there. It's like this. There's no way to get around it. What you see is what you get, right? And that's one of the things that's really interesting about this approach to computation. There's no hidden extra state that you have to keep around in your mind in order to understand how the thing behaves. It's all in the structure. And that's sort of the essence of bisimulation. Bisimulation is capturing the content of the structure function relationship in not just the pi calculus, but in all of these computational calculi that have this property. And so now that now what we're saying is, hey, that structure function relationship can yield interesting information about structures like knots. So outside of computation, physical structures, right? Or at least physically realizable structures. And that was the other thing that was really important about this work, was to try to say, hey, pi calculus isn't just for computation anymore. We can use it to reason about the physical world and physical dynamics, which was another underlying point of doing the work that I did with David, was that it isn't just about computation. Or put a different way, if you wanted to go after Wheeler's it from bit program, here's a tiny baby step in that direction. How do I get from computation to a manifest physical world? And here's a baby step that will do that. I just plunked down a lot of information all in one rant.
I agree that this structure function relationship is an important thing, and we're, this bisimulation is kind of capturing that in a really essential way, and I see the importance of trying to bring that notion over to different areas of mathematics. I mean, that totally makes sense.
Yeah, but in particular, I like, again, if the physicists really are serious about trying to get a physical universe arising out of computation, then ultimately they're going to have to deal with exactly that, the structure function relationship, right? And bisimulation says something really essential about that. And so so going and exercising these kinds of ideas in sort of these very nicely constrained toy problems like ambient isotopy, which is not so much of a toy, right? I mean, David's history just shows us, how subtle it can really be.
Right.
Right, but it's so much simpler than trying to model, what it's like to chase a dog through a park, right?
Right. So much. It really is. It's amazing how difficult it gets so quickly,
That's exactly right. That is precisely right. You know, and anyone who's like had, you know, 2 or 3 dogs meet in a park and they're all on leashes, they know precisely how tangled things can get.
Yeah, right. That's for sure. Especially Australian shepherds, I think.
Yeah. Oh my God.
Yeah. They've got a lot of energy.
They certainly do. They
Yeah.
certainly do.
You know,
So,
I've been kind of thinking along similar ideas, I guess, but probably from a slightly different angle. But I don't know if I have it as well formed as you do, because obviously you've thought about these things much more deeply for much longer. But just that how mathematicians tend to get stuck in this thing. Well, some of them do think of a function as rules. Like I'm going to color it this way: functions as rules versus the graph of a function. So, and then, you know, kind of one's more dynamic than the other, I'll say anyway. So. And how this kind of, I think there's kind of a tendency in modern mathematics to kind of just focus more on that function as a graph, and you lose something, you know, by doing that. I mean, obviously there's a lot of power in that too, but
yeah, agreed.
so yeah, I think you're onto something here, really. You know, this is going to be, you know, we got to keep pushing on this one. So yeah.
I agree. Yeah, exactly. But one thing I want to do, I didn't have a chance to do it since last week, was just to revisit the encoding, but really use row calculus as opposed to pi calculus, and see if something changes. Because the square root calculation absolutely did change when I went.
Right.
Just real quick to clarify, in the context of bisimulation, what is structure and what is function?
So the structure is the structure of the term, and function is the evolution of the term.
Oh, okay.
It's really interesting because it's very hard to get mathematicians who are outside of the computational realm to understand the payoff. The payoff that you can use the Hennessy-Milner logics to go and do classification.
Right, that's for sure.
For the mathematicians, what I've discovered is for the mathematicians to grok this, you know, there's this whole other line of work that has to be done to go and do a bunch of classifications, like classify various versions of knots, you know, various families of knots with these formulae, which is a whole extra line of work, right? I mean, to me, it's already interesting just to have this cool theorem. And then just point out that when you put the two theorems together, the one about bisimulation corresponding to logical characterization and the bisimulation corresponding to ambient isotopy, when you put those two together, then you get this classification scheme, right? But in order to be received by the mainstream mathematical audience, you have to take this additional step, which is to go and classify different families of knots using the Hennessy-Milner formula, and I just never had the time to go and do those calculations. It's a lot of work, right?
It is, yeah. And I'd say it was kind of the same here. I've got these other projects that I had to work on, but I'm excited to come back to it though. So I've been meaning to do it. It's always been there. But,
that's right. I understand.
But now I have time, I think. So yay.
Well, that's good.
Yeah, I was going to say I'm excited about the row calculus too. Like I know I'd probably looked at the paper that you and Matt had written, like, well, I don't know, it was a long time ago, over 10 years ago, but
2005. Yeah, that's right. It's like,
and I had a lot of background information I guess I needed to assimilate to really understand what was going on in there. But I feel, I reread it last week after that root of processes posting you had, and so yeah, I'm very excited actually by reading that. Now it's like, oh, I kind of get what I'm getting from this. So
that's awesome. Well, that's good to hear. We'd like more mainstream mathematicians to have that response to the row calculus paper.
right, yeah. Well, someone will be like, oh, how's it going to benefit me? There's always that aspect of it too. They're so vested in their own research programs, and anything that's going to either take them aside from that or threaten that, on some hands they might not react so well sometimes, but hey, you can't stop the truth from coming out. So
that's exactly right. I think science and math proceed at a particular pace, and hopefully that pace is mostly governed by the process of pursuing the truth, which in the case of science is the scientific method. In the case of mathematics is the the publishing and reviewing of proofs. It is slowed down quite a bit because, people have tastes. People want to, look at proofs that are, in areas that they're interested in, right? Or have, I don't know, certain kinds of popularity or other kinds of aspects which garner the attention. The process doesn't proceed exactly ideally.
Right, right, exactly. Yeah, that's for sure.
But it is, I mean, as Christian and Isaac and I talked, it is a different kind of governance model, right? When a community is interested in the truth, the kind of governance that you get is very different. So that, it has that going for it for sure.
Right. And I think there's probably will be a shift coming up here with, I don't know if you all know about like the Homotype type theory or Homotype type theory, I think I go. And so I think there will be some shift and actually some more, I guess, I see it as unification of, computer science and mathematics again, kind of getting closer together like they were maybe more so at the beginning of computer science. So.
I think you're right, and I'm delighted that the Homotype type theory is getting the kind of attention and engagement that it is. To be honest, I have the Ladle program proposes a completely different notion of type, and so at some point I really want to look at, compare and contrast notions of type from Homotype type theory from the.
That'd be interesting.
Yeah. I think it's. Because again, I think Homotype type theory is still beholden to or captured by a notion of function.
Yeah,
and
I agree. I agree with that.
Yeah, and function is just it's not the only game in town. And in fact, if you look carefully at most computational phenomena, it's very far from what goes on. Right.
Right.
We have lots and lots of intuitions about functions, but nature has other ideas about how to scale.
Right. Exactly.
You say you want to expand this knot idea to the row calculus. Does reflection add a whole other aspect or dimension to that interpretation?
Well, one of the things that I was always really interested in was the kind of recursive knot idea, or tower of knots, where inside the crossing you have another knot, and or not a knot but a tangle. One of the ports coming in, you could fray that wire into a bunch of different wires, right? And those wires could all be intertwined or tangled, right? And then at any one of the crossings of those wires inside this crossing, you could do the same again.
Have you ever seen that picture of the Alexander Horn sphere, by the way, where
exactly?
I mean,
yes.
It's kind of something like that.
Yeah, that's exactly right. So it becomes a recursive or fractal-like construction. In the same way that, remember in the spring we talked about the sort of tower of computations. In the tours of living, you can apply the same idea to knots, and so you can make them sort of, instead of stopping at a crossing, you can kind of virtualize what the crossing is.
Sorry, could you elaborate on that just a little bit?
There's a way in which every knot corresponds to a braid. So the braid has endpoints, some endpoints at the top and endpoints at the bottom that are open. Right, so you could think of every crossing in a knot as like a braid. In fact, you can generalize it from a braid to a tangle, where the endpoints come. When the signal comes in, it doesn't remain as a single wire; it gets frayed. Inside a particular crossing, you could have arbitrary complexity of a tangle. Is that making sense? Can you visualize that?
Yeah.
And then inside that tangle, you have a bunch of crossings. And those could also be tangles. And
I think if you Google like Conway tangle, there'll be some pretty decent explanations of it too. some good pictures. I think a picture is worth 1,000 words.
That's exactly right. And so with the row calculus, because you have reflection, you can model that, right? So whatever channels you're using for the signals coming in, they could turn out to either be or transport things that are tangles at the crossing level. And so the reflection of the row calculus gives you an edge or an angle to express these sort of recursive knots. Those beasties are more satisfying to me because I don't have to have any atoms, or I can because in some sense the crossing is like an atom, and I always like to boil away the atoms if I can.
Right.
The intuition goes back to Greg Chaitin. Greg Chaitin was certainly a mathematician after my own heart. He points out that wherever you have atoms in a theory, whether it's axioms in a proof system or elements in a FM set theory, or wherever you have these sort of unexplained set of gadgets that you start off with as your ground, that represents the risk of your theory. And so I'm always trying to minimize the risk of the theory, right? That's the idea.
Yeah, it's a good way to think about it.
Yeah, that's really all the row program does. The reflective program is just about minimizing that risk. So you can know exactly where the ground is. Like in the case of row, the ground is 0.
Mm-hmm.
That's your only risk. The idea of 0 is not too much of a risk. I mean, it's a little bit of a risk.
Right.
but it's not as much of a risk as an infinite set of names that has this essentially unrealizable problems.
Right.